Hello, everyone. Hope all of you enjoyed lunch. My name is Yibing Xie. I'm from Cedars-Sinai Medical Center. I'm here with my co-moderator, Su Wai, and from Northwestern University. It's our pleasure to present you the next session of the AI for vascular imaging. And the first talk, educational talk, will be given by Professor Markl from also Northwestern University. And the topic of the talk is AI for flow imaging. Michael, the floor is yours.
Thank you very much. Welcome everybody to the afternoon session. I'd like to thank the organizers for inviting me to talk today about AI for flow imaging. So these are my disclosures. So if we think about flow imaging, and this is here an example of the thing I've been involved with over many years. This is 4D flow MRI. And as you can see here, there's really two aspects if you think about flow imaging and where AI could actually make an impact. And one is really the acquisition side of things. So where you could look at AI for coming up with different concepts for imaging acceleration and reconstruction. I will talk about this. And another large aspect, and this is probably where in flow imaging most of the focus has gone so far, is looking at data analysis and imaging enhancement. So I'll go through these different kind of aspects of using AI for flow imaging step by step. And I did a little bit of a literature review and search, and I apologize if I cannot cover all the literature in this very dynamically evolving and fast moving field. So maybe let's start with 2D phase contrast imaging or two-flow imaging. There's actually a large body of work out there now trying to, number one, accelerate 2D flow imaging, but on the other hand, also looking at improving and automating, in particular, the image analysis. This is an example of one of these papers here on the right, and they used a deep learning technique to reconstruct 4D flow data and compared it to compressed sensing. So this is really an alternative way of reconstructing subsample data but using AI instead of compressed sensing. And what they found, and this is kind of a common theme that you'll be hearing, is that AI actually allows for higher accuracy for peak velocity quantification. There's an underestimation or kind of a filtering effect associated with compressed sensing and total flow, and also for improved reconstruction time. A larger body of work has really gone into kind of 2D phase contrast analysis, and you're very familiar with this. Typically, you would draw contours around the vessel of interest and then quantify things like net flow or peak velocity. This is a study here that looked at fully automated analysis, and actually it's a very promising result. This was a software-based approach. Close to 100 patients were included, and you can see that if you look at flow quantification in the ascending aorta and pulmonary artery, there was actually an expert level quantification, fully automated, possible in 93% of cases. So very encouraging. And also if you look at the correlation plots, you can see there's really close agreement with manual analysis. Now what I really liked about this paper is that they also showed where the cases where the AI actually failed. And you can see this here on the top right, where you can see that the contouring actually didn't identify the vessel or incorrectly identified the vessel. And I like this kind of honest publication where you can actually see where the technique fails. So very promising, but I think at this point in time, not really ready for prime time to fully automated analysis, but certainly very important and very critically helpful for workflow efficiency improvements. You can take a step further, and this is a slide that has been shared by Ning Jing from Siemens, where this whole process of automated analysis is now moved from a software package directly to an inline process on the scanner. And that, of course, has several advantages. And here's a nice example where you can see that right after the acquisition on the scanner, there's contouring and then kind of quantification of flow time curves. So a lot of potential there to really kind of at the scanner directly get analysis available. Now moving to 4D flow MRI, there's actually also be a large body of work in terms of using AI for image reconstruction. This is work from Harbin Barhane, one of my grad students, and he presented this at SMRA actually 2 years ago. And what he did here, they took compressed sensing accelerated data sets, was 18 patients, and they received 4 4D flow scans, 3 highly accelerated scans, and 1 conventional 4D flow. And then he trained a network to do the reconstruction instead of with CS, also with AI. And the key results here are that CS is still an iterative computationally intense reconstruction, and AI, while training the algorithm, takes a long time and lots of GPU power, the actual execution of the network is very fast. And this is not unique to this kind of application. It's kind of a general feature of AI. And you can see the AI reconstruction was faster than the original kind of CS reconstruction, but also very important, it has had less underestimation and peak velocity compared to CS. So there seems to be less of a averaging or filtering effect with AI compared to CS. He's since then kind of taken that a little bit further, and you'll see this later in the session. Haben has a talk here. This is just a preview of some of his results where he now kind of drove the acceleration even further up to 16-fold and had very good results, and even moved away from the compressed sensing type pseudo-random undersampling, but just did a very simple center cropping of k-space and still got very, very good results. And this has also been shown by another group. This is an example here from Sebastian Korserke's group at the HEH in Zurich, where they also kind of did an AI versus CS comparison and a 4D flow type of approach. And you can see here similar results. Recon time was 30 times faster compared to compressed sensing. They could get higher acceleration factor, and they could really nicely preserve pathological flow features that were seen in the reference data set. So I think very, very promising results here for AI. That more work is needed. One of the limitations of most of the data that has been presented to date is that it's really limited to a single acquisition technique, single center, single vendor, single type of protocol. Arriving at techniques that are versatile across different acquisition methods, different case-based sampling patterns will still require a bit of work. Now, moving on to data analysis. So if you think about 4D flow analysis, it's really a multi-step process. There's typically pre-processing, such as eddy current correction and velocity aliasing. Then there's a 3D segmentation approach. And then you kind of, only after that, you get to the 3D visualization and quantifications. And if you look at this process here, I kind of put some times to it. So this is really about 15 to 20 minutes that you typically need for this type of analysis and very efficiently organized workflows. If you have software that's reasonably well integrated, and if you can do away with the segmentation process, which is the longest, you can probably do it in 5 to 10 minutes for simple analysis tasks like here, for example, shown in the aorta. But if you talk to the clinicians, at least at Northwestern, where I'm from, if I've talked to the attending radiologists and others, I'm told that the time that they can afford really for 4D flow analysis is really not more than 2 to 3 minutes. And this is really driven by their experience. If they do 2D flow analysis, that's how long it takes them to get the data. So if we with 4D flow take longer than 2 to 3 minutes, they may not consider this as a viable technique. So this really should be the goal, to get the recon time down to 2 to 3 minutes. And again, this is where AI comes in. He's worked from our group using AI for velocity anti-aliasing compared to standard algorithm, where we could show that this works really well and actually is able to detect more aliased voxel compared to standard algorithms. This is work by another group just recently published in radiology out of USD in San Diego, where they applied this to abdominal imaging and had very good success with AI-based velocity anti-alias, and again, fully automated and improved performance compared to the traditional algorithm. Same there is true for other kind of pre-processing steps, such as 3D segmentation. Here an example of an algorithm that was trained on about 1,000 4D flow data sets of the aorta, where you can see, if you compare the manual and the AI 3D segmentation, that's fully automatically derived from a phase contrast angiogram directly calculated from the 4D flow MRI data. You can see there's very good agreement between a manual segmentation, which took on average 11 minutes, and the AI-based segmentation, which really only takes 1 second per data set to perform. And particularly if you look at also the flow quantification based on the 3D segmentation contours, they're very similar between the manual and the kind of AI or automated segmentation. Another example from the group in Linköping, where they took this further to fully whole heart 3D segmentation, and really also segmenting out the individual compartments of the heart, the ventricles, the atria, the pulmonary artery, and the aorta. As you can see here, with very, very good results, really good DICE scores, and also very good comparisons of the kind of ventricular volumes and ejection fractions and stroke volumes and so on. So if you go back now to the kind of workflow we have for 4D flow analysis, pre-processing, velocity anti-aliasing, 3D segmentation, you can now replace all these manual steps with a series of successfully deployed AI networks that take on these tasks in a fully automated fashion. And as you can see here, we did a study at Northwestern and over 1,000 data sets, and found that while this worked actually really well, you can see the ROC analysis for the different pre-processing tasks, and while the standard manual analysis took about 15 to 20 minutes, you can now do this in about 30 seconds. So this is really an improvement, and can then be followed up by flow analysis, where you still may have some manual interaction, but this probably gets you much closer to the clinical goal of doing everything in about 2 to 3 minutes. And once you have a kind of tool like that, or kind of an automated workflow, and by the way, you can also automate things like plane placement shown on the right and peak velocity extraction. You can use this actually in multiple ways, and one way is what Ethan Johnson from our group introduced yesterday. You can use this for large cohort analysis that's very reproducible because it no longer has any manual interaction. So you just construct a list of subjects who had 40 flow MRI, then you hit click a go button, and then you can have a kind of successive execution of all these algorithms that do all these tasks automatically, and you can very flexibly, quickly crunch through large data sets, and I mean, this is more from a research perspective, and study 40 flow hemodynamic parameters in larger cohorts. And again, one of the advantages here is if you rely on these algorithms, obviously you need to include some quality control checks, but then there is really no or very minimal manual interaction, so the observer variability in these large cohort analysis kind of goes away. Another option is, and this was also shown yesterday already, is with these type of tools, you can bring it directly to the scanner. And there's the colleagues at Siemens have developed this FIRE framework, which lets you kind of implement these type of algorithms directly in the scanner very flexibly with different type of coding languages. So you can use Python or MATLAB or similar type of approaches. And the idea here is that on the scanner, the data is taken out of the reconstruction pipeline. You can do your processing, and then it gets injected back in. The advantage of this approach compared to other approach is that it does not need any extra hardware. It just uses whatever CPU and GPU power or compute capabilities the scanner has. So this is an opportunity obviously to do this, and this is something we did at Northwestern as well, and this is really on scanner, fully inline, fully automated 40 flow analysis directly on the scanner after the scan. You can see here the magnitude image, phase difference image, and then automatically performed eddy current correction, 3D segmentation of the aorta, anterior maximum intensity projection. This has recently been developed further, again by Ning Jing from Siemens. I think this was also shown yesterday, and she's really trying to take this now to the next level with not only the very straightforward, simple visualization of peak velocities I showed here, but also with automated plane placements, flow volume quantifications, and tables that come out here. I just want to, be careful not to sell this as being readily available. This is still very experimental. It's probably very sensitive to the type of 40 flow MRI protocol. Certainly needs more validation. And obviously, this will not replace any vendor solutions for 40 flow analysis software. You will still want to be able to interact with the data after the scan. But I think this is a great opportunity to do quality control directly at the scanner, give feedback to the technologist, and maybe get some early results, and then guide the secondary analysis that may be done by the radiologist or by the cardiologist. So I think very promising results here, and certainly more to come. And finally, I just want to kind of point at one other area where AI becomes interesting. So instead of using it for kind of accelerating the imaging, kind of subsampling the data and then reconstructing it, you could also use it for resolution enhancement. So you do a kind of fully resolved scan, but then use AI to kind of achieve resolutions that you wouldn't otherwise be able to do without kind of increasing the scan time to kind of tens of minutes. And this is a nice work here by Alistair Young from London, where he showed that he can enhance the 40 flow spatial resolution and reduce noise by using high resolution computation fluid dynamics as the ground truth data for training these type of networks. And you can see this nicely if you compare the original and the fully resolved data. This has recently also been applied by almost a consortium, I would say, of different groups at the University of Greifswald in London and also Michigan, where they used this to achieve sub-millimeter, 0.5 millimeter high resolution intracranial 40 flow MRI. And that really then set the stage that you had high enough resolutions in these small vessels so that you could apply really fluid physics type of approaches then to also pressure gradient and pressure quantifications on that data. So also very promising new approaches here that are not really focused on reducing acquisition time, but really enhancing the image quality and the resolution. And that brings me to the end, so I hope this was educational and useful. There certainly is, as you've seen, a large role of AI for 4D flow imaging, both on the image reconstruction and data analysis side, but also resolution enhancement. And I think in the future, we'll see probably the whole pipeline that has a lot of AI, starting from data acquisition all the way to the reporting of the results. Thank you.
Thank you, Markl. This talk is open for questions. We have time for a few questions. Maybe I can get started. Markl, so yeah, it's great to see AI is making an impact on many aspects of 4D flow, starting from acquisition, acceleration, recon, and analysis. In your opinion, what do you think is the areas that the field should work on to really help push 4D flow to more wider clinical adoptions? Because it's still a lot of people, clinicians are saying it's very complicated. So what's the priority?
I think the one priority is if you've ever sitting in at a workstation where you need to do a 4D flow analysis, you typically need to wait 5 minutes and the data has loaded and it's pre-processed. And this should be completely under the hood, kind of almost a black box approach, and should come off the scanner like that. So if you could, at least the pre-processing all done on the scanner before somebody even looks at it, I think that would cut so many minutes of the analysis and would also make it much easier to use. So that's number one. And I think the second important point is there's been good progress with kind of 3D segmentation and things like that, but reliable identification of anatomic location and automated quantification, or at least basic flow parameters, would be helpful. So I would envision this: you go to the reading room, 4D flow scan has been done, you press a button, and then you see the aorta with the planes already placed and the flow time curves right there. And the only thing you need to have to do is kind of adjust the planes a little bit if you're not happy with the location. And then you can, this obviously does not work if you look at congenital heart disease or complex cases, but for the bread and butter heart valve disease cases, I think that could certainly, make it much more clinically feasible and efficient.
Okay, let's thank our speaker again.